I'd like to thank the organizers for organizing this conference and for inviting me. This is a joint work with Henri Elad Altman, who is going to talk after me on the same topic, so continuation. Okay, so let me start with Bessel processes. So in fact, the squared version. Let's see. So this is the SDE in R. So in fact, in R+, you fix some parameters. So delta, which is essentially plays the role of a dimension. Y is the initial condition. Both are non-negative. B is a standard Brenner motion. Then this is the SDE by Yamada Watanabe's theorem. Since the diffusion coefficient is at least 1/2 Hölder, then you have existence and uniqueness of a strong solution. And moreover, it turns out that the solution is always non-negative. So you can forget the absolute value here. So it turns out that these processes have many beautiful properties. You can compute many things explicitly. For instance, the transition semigroup, which contains some special functions of Bessel type, and that's the reason why the name Bessel is associated to these processes. And okay, there is an important paper in the 80s by Pittman and Yor, which started a very, say, important production. And you can also see the monography by Reviews and Yor for many informations about this class of processes. Now, in fact, the Bessel process is the square root of the squared Bessel process. It is defined like this, which is okay because yt is non-negative. Now the question is, what is the equation that x satisfies? This is not completely obvious because the function y to square root of y is not smooth at 0, and the Ito formula cannot be applied too naively. Okay, so let's see. At least for delta strictly greater than 1, one can show that the Ito formula essentially works correctly. And this is the SDE, if you want. This is the semi-martingale decomposition of X. So initial condition square root of Y plus a drift of this form, delta minus 1/2 times 1/x, plus again Brownian motion. So this time the noise is additive, but the noise is more difficult than for the square version. So in fact, again, xt is non-negative, of course, because it is a square root of a non-negative process. And by the Ito Tanaka formula, you should also include this local time term, where now the family, so here this is L0, so it's the local time at 0, and LAT is defined by the occupation time formula for the semi-martingale X. So it is you can prove that this family exists and that it is bicontinuous in T and A. But okay, in fact, in this case, L0 is 0. So that's why you do not necessarily need to write it. But okay, for what is going to follow, it is important to know that in principle you might have another object here. Okay, just let me remind you, LT0 is a process which is continuous in time, and it grows only, so it is a monotone non-decreasing, and it grows only when x visits 0. Okay, so that's why it's called local time at 0. So, but this works only for delta strictly greater than 1. So let me mention, I'm not sure that, I don't remember. Yes, I say it here. So let me just say it immediately. When probably you know very well that for delta greater or equal than 2, x does not visit 0 at positive time. While between 1 and 2, x does visit 0, so 1 over x is maybe bad, okay, maybe infinite, but at least this will be L1 in time, okay, so the drift will be well defined. So you need to take into account these details. Why? Because when delta goes to 1, in fact, this will blow up. So you may or not have a local integrability of 1 over x depending on the dimension. Okay, so in principle this is said here somewhere. So let's see. For delta greater than 1, the drift is dissipative. Okay, by this I mean just decreasing in this case on R+. And this implies that the SDE has pathwise uniqueness. And in fact, you can prove that the solution is strong failure. So pathwise uniqueness is very simple. So you take two solutions, xt minus x bar t square. Sorry, let me go back. It means that they are driven by the same bt, which cancels because the noise is additive. So you differentiate, and here you get, well, 2 delta minus 1 over 2 xt minus x bar t, and then you have 1 over xt. Okay, so I think this is correct. And since this function is decreasing and delta minus 1 is positive, here you have the good sign. Okay, so this is, and since it is 0 at time 0, it stays 0. Okay, so the argument is essentially this one. It's very simple. But you already see why I say that everything works well above 1, but maybe not below 1, because the same argument gives the opposite sign when delta is less than 1. So okay, one sees that for small delta, things may get substantially more difficult. So let me go back to my slide. At least for delta greater than 1, things are relatively good. So x is known as a Bessel process. As delta goes to 1, the solution converges to the reflecting Brownian motion. So now this term, you see, I was saying before, when delta goes to 1, this goes to 0, but this blows up, and the result, so 0 times infinity, so in fact gives a process which is like L0, and now L0 is not 0 anymore. So it is a monotone, non-decreasing continuous process, which is null at 0, and x is continuous or negative, and you have this condition. So again, L increases only when x is 0. So I was saying for delta greater or equal to 2, almost surely xt is positive for all t. So now the almost surely and the for all t are in the good order. Okay, so this is you fix the realization. Then for all time, you do not you never hit 0. For delta between 1 and 2, you hit 0 almost surely for some positive time, but still the local time is 0. So this is what I said before. So this may be strange. It means that this is, so the semi-martingale local time is not the correct scale. So you can define a different function, family of local times, which are called the diffusion local times, in this way. So in fact, if you compare, it just means that capital L is equal to this small l times a to the delta minus 1. So capital L0 can be 0 without small l0 being 0. Okay, so you see that there is here a limit, okay, which is so. In fact, in this situation where delta is between 1 and 2, small l t0 is the limit when a goes to 0 of, okay, so this goes to 0, but it is divided by something which goes to 0, and you have a non-zero process. Again, many things are known. You can prove that L0t is the inverse, so the right inverse of a 1 minus delta over 2 stable subordinator, so an increasing Levy process, which tells you many things. For instance, this tells you that, so you take the set of zeros of x, okay, so you take the random set, the t such that xt is equal to 0, so this is a random set, and so the Hausdorff dimension of this set will be almost surely 1 minus delta over 2. Okay, so okay, all this is again classical, although not so well known anymore in a sense, because it's never taught in courses, but okay, it's available in the literature. Okay, now we are still above 1. We have included delta equal to 1. So what happens when delta is less than 1? Okay, in this situation, okay, look at first this second formula. You have to write your equation like this. So you have the same drift, but the local time is not 0 anymore. In fact, it is infinite. So let me correct this sentence. In fact, in this situation, x is not a semi-martingale. So the theory of existence of local times does not apply. What works instead is this definition of diffusion local times. So in fact, let me tell you, it turns out that you can write always xt as some nonlinear function, say some psi of some Brownian motion, so it's not the same Brownian motion, say b bar, with a time change. So this is always true for one-dimensional diffusions. So in a sense, this allows to construct diffusion local times for x starting from the local times of the b bar, but they are not exactly the same. So you have to add this density on the right. And now, okay, you see that the formula can be read now in the other sense. So L0 will be the limit of LAT times a to the delta minus 1, but now this diverges. So because delta minus 1 is negative. So you do obtain that the standard local time is infinite at 0, while you still have a good process if it is defined in this way. So again, small l is a bicontinuous family of increasing processes, etc. Okay, so notice that this is positive, infinite. So delta minus 1 is negative. This is also infinite. So these two terms renormalize each other. And in fact, it is possible to write explicitly the result. It is like this. So you integrate, so you use the occupation time formula. The LTA over A times a to the delta minus 1 is this term, and the minus LT0 times an infinite constant is this term. Okay, so but you regroup them together. You have to prove that LA is essentially Hölder in A in such a way that here you gain some power of A, which makes this integrable at 0. Okay, so this is a quite, say, interesting phenomenon. And so as far as I know, there is no approach, okay, to this SDE, no direct approach. Okay, I've never seen a formulation which says, okay, take this SDE, the solution is defined like that, theorem, existence, and uniqueness. Okay, I've never seen this. So what you do is you prove that if something is okay, satisfies this and this is good, well defined, you take the square, you go back to the equation of the square Bessel process. This has a pathwise uniqueness. Okay, and then okay. Now I have mentioned the strong failure property, so I don't want to define precisely what this is, but I said that it works for dissipative drifts, for decreasing drifts. Now the drift here, okay, it's very increasing, in fact, and then there is this. So in fact, yeah, in fact here you have one term which is positive, which is this one, because now delta minus 1 is negative, plus another term which is negative and comes from the local time at 0. So in fact, you don't know the sign anymore. Okay, so this simple, okay, I was kind of confusing you before when I said that you would have a positive value. In fact, you don't know. You have two terms with different signs, and you don't know exactly the result. Okay, now strong failure property, in fact, holds also for this process for delta less than 1, uniformly in delta. So this has been proved by Henri, although he's not going to discuss this. Okay, this is quite interesting, and okay, I will come back to this for the SPDE case. So again, if you go if you look at this equation, you see no transition in delta. Delta greater or equal to 0 plays the same role. Okay, 1, 2. You don't see why these are special values. While okay, this equation looks more dependent on delta, and you see that you have to introduce the scale, etc., etc. Okay, and again, so there is this renormalization phenomenon which has been, say, studied a lot in SPDEs, in regularity structures, etc. Here it appears in a diffusion in one dimension. And so on one hand, it's quite different. On the other hand, there is some similarity. So regularity structures are based on Taylor expansions. So this is essentially a Taylor expansion at level 0 of the local time, okay, in A. So yeah, Jonathan, you will see. Okay, so this is more or less what I wanted to say about Bessel processes, and now I want to discuss. Yes, no, there is another property which is very important, which is scale invariance. So it is known that the Bessel processes are have the same scaling as a Brownian motion. Okay, so x. Okay. So apart from the initial condition, it gets also multiplied by 1 over square root of lambda, but the equation is invariant under this scaling. Okay, so same as the Brownian motion. Okay, let's see. Now, Bessel-like SPDEs. So at first, okay, let's say at the beginning there was just this equation, which is the Nuallard-Pardue equation, and so it is a SPDE plus some reflection. So this psi is space-time white noise. We are in say an interval 0, 1. So space is one-dimensional. The solution is continuous. It is supposed to be non-negative. Yes, R plus. Eta is some measure, and like so, the local time at 0. So it is supposed to have a support in the set of zeros of U. Okay. Okay, I have a small simulation. Let's see. Where is it? Okay. No. So it works on my computer. So. Yes, good. So this is the stochastic heat equation with additive space-time white noise. Okay, so it is, yeah, so it is this equation without reflection, okay, just the standard stochastic heat equation. So this is the absolute value of this function, okay, and this is the reflected equation. So yeah, so you see that they look quite different. So both here are positive, so you can ask yourself what are the, in particular, the heating properties. These are the most interesting okay, questions. Okay, so let's let it run. So what is view? Don't remember for screen. Okay. Yeah, so it turns out that the invariant measure of this SPDE is the 3 Bessel bridge. So we get a connection with the previous class of processes. So again, so you should think of the time of your Bessel process to become the space of the SPDE, and then you have an additional variable, which is the t here, so the time which flows. So in space, this equation produces essentially a 3-dimensional Bessel bridge. Now then, I asked myself, so already a long time ago, what is the corresponding equation for delta Bessel bridges with higher dimension? Well, actually, I asked myself for any dimension, but I could answer for delta strictly greater than 3, and it turns out that you have this form. So, well, the delta minus 1, delta minus 3 over 8 is kind of mysterious, but The delta minus 1 reminds of the delta minus 1 which was in the Bessel process. So instead of 1 over x, now we have 1 over u cube. But it turns out that this is natural because so this equation has the same kind of invariance under scaling as the stochastic heat equation without drift. So in this case, this becomes, let's see, 1 over lambda to the 1/4 u. So here you have, no, I'm messing up. So in, no. So this must be this. In space, it's the Brownian thing, and in times, this is what? I think this is correct. Okay, so if you replace, so if you check the solution, the equation satisfied by this function, it has the same form. Okay. So usually when you have scaling invariant equations, they are interesting, okay, because they are kind of fixed points of some map. So, well, I introduced this. It turns out that something like that had already been studied. I proved that if you write the coefficient like this, the delta Bessel bridge is the invariant measure of this process. So note that, of course, for delta greater than 3, the coefficient is positive, and therefore, again, the drift is decreasing. Okay, this is again very important. It makes life easy. For instance, you have this simple argument which you can adapt for uniqueness, etc. Okay, but so I defended my thesis in 2001, and this was done at that time. And for a long time, I did not know how to go below 3. And you see the analogy with Bessel processes. So it's really the same. There, the transition is at 1. Here, the transition is at 3, and there may be other transitions. Yeah. So, yeah, what about delta less than 3? So this question has been open since 2001. Let's see. So let's try to go below 3. So we consider this drift. I write it in the integral form. And I have this coefficient. And again, okay, I say maybe we have local times. So it turns out that the correct choice is, again, diffusion local times. This is not a diffusion, of course, but you see the analogy with delta Bessel processes. So this is the family that you need. And for large delta, at least, so you can write this drift. So you apply, you see phi here is 1 over a cube, okay? You write this. Now, when delta is less than 3, you see that here you have a power which is strictly less than -1. And so, sorry, less or equal than -1. And therefore, at 0, this is divergent, okay? So for delta greater than 3, this makes sense. But for delta less than 3, it does not. And again, it's the same as for Bessel process. So we may need to change, so we have to change our drift. And so in analogy with Bessel processes, so you write a kind of renormalized version of the drift as follows. 1 over a cube, so LA minus L0, blah, blah, blah. Okay, now of course, you need some Hölder regularity in A, which is not completely obvious, but if it is the case, then you gain a power of A, which makes this integrable at least as long as delta is greater than 2, because when you go below 2, in fact the same problem arises again. So in fact between 1 and 2 you expect to go to the next order, okay? So this becomes a true Taylor expansion, and yeah, okay, you expect this. So in fact, it turns out that the derivative of the local time in A, so not only is expected to exist, but it is expected to be 0. So in fact, the same expression holds for all delta between 1 and 3, which is, okay, somewhat surprising. So, okay, so stay with me. So again, you are now inspired by this idea of Taylor expansions. You think you need to go to the next order, but it turns out that this function tends to be, say, of order a square around 0. So you don't, in fact, this term will be 0. Okay, now when delta goes to 1, the previous expression becomes essentially a second derivative in A at 0. Okay, so I'm going to explain this a little bit better in a second, but at least I can write the form of the SPDE for delta equal to 1. So my kind of strange drift has become this. So it is a second derivative in A of the local time, of the diffusion local time at A, and then setting A equal to 0. And then, okay, this is the derivative in time, which is standard. Now this, the case delta equal to 1 is the most interesting, and it is motivated by scaling limits of critical pinning models. So again, this is something which has been a problem which has been around for 15 years, more or less. We do not know how to solve this, but it is expected that this equation is the limit of some discrete model, okay? Now, okay, and then you can also go below 1, and this time you expect the second order Taylor polynomial, which is not 0 this time, and yeah. Okay. Now let me just explain you one thing which can probably motivate what I've been saying until now. So for alpha positive, define this measure. So it is x to the alpha minus 1 over gamma of alpha times indicator function of positive numbers in the x. So there is a very nice way to extend this to negative alpha. So for alpha 0, this will be a Dirac mass at 0. For alpha negative, so when minus alpha is an integer, you have a derivative always at 0. So these are distributions, but they are perfectly well defined. And when alpha is negative but not an integer, it is this distribution, so it is the same integral, but you have to subtract the Taylor polynomial at 0 in such a way that this function has the correct behavior at 0, which compensates the diverging integral here. Okay, so again, this is very very close to what happens in regularity structures, but it's very classical, in fact. So said like this is called fractional calculus. Okay, so in fact, this is what we are doing on the SPDE, but the function phi is the local time of the solution. Okay, so in fact, if you want, you can write the SPDE for all delta in this unified way. So this is the drift. For delta greater than 3, it just reduces to the standard object. And for delta less than 3, as you go down with delta, you increase this length of the Taylor polynomial. Okay. Now, in fact, most of the above is conjectural, okay, in the sense that we can do something, but most was kind of dream for the future. So what is really proved and new, and what has allowed at least to guess this formula, is an integration by parts formula on the law of the delta Bessel process, and this will be explained by Henri. So this tells you the form of the equation. So if you manage to construct a process, then it must have that description. So how do you try to construct such a process? So by Dirichlet-Formes methods, in principle you can. For the time being, we are reduced to just the integer dimensions, but delta equal to 1 is the most interesting one. So it is not so bad as a start. So Dirichlet-Formes give you a method to construct Markov processes, which can be weak solutions to your equation, blah, blah, blah. So you have something. It is not yet the end of the story by far. So in fact, you would like the following. So by decreasing a number of question marks. So again, by analogy with Bessel processes, you expect that some form of pathwise uniqueness is true, okay? But this is completely outside the present technology. So there is this problem of existence of local times for solutions to such SPDEs. This is extremely, in fact, strange. No one knows, at least no one that I know knows how to prove that solutions to SPDEs have local times. So let me tell you that this is very strange, because the rougher your function, the better your local time is. Okay, so but in fact, the local times are, with the present technology, reduced to semi-martingales or diffusion in one dimension. Okay, so but morally we should have local times, but I don't know how to prove this. The strong failure property, which I have not discussed in detail, but again, it should work, I think. No, I don't know. No, this is too much. It may work. Henri proved that for Bessel processes, it does work uniformly in delta. So it's a very, say, inspiring result, but I have no idea. And okay, the associated Dirichlet-Formes, I said, are under control in the integer dimension, but they should be under control for all delta. But for the moment, I don't know how to do this. Okay. Now, let me, again, pathwise uniqueness. I said it before, I repeat it. For Bessel processes, you take the process, you square it, and then the Ito formula tells you what is the SD satisfied by Y, and the Yamada-Watanabe theorem gives you existence uniqueness for Y, and therefore for X. Okay, for space-time white noise SPDEs, Ito calculus is difficult. Okay, so Carlo, who is here, is investigating this with the regularity structures, but okay, before we get to a theory like this one, okay, we will have to work, so Carlo will have to work a lot. Now, let's see what this might give in this setting. So the drift here is proportional to u to the minus 3. Then it seems reasonable to, okay, instead of squaring the solution, to take the fourth power. Now the equation satisfied by u to the power 4 is this one formally. So you're happy. Now the drift is just constant, like for square Bessel processes. Now you have gained this crazy term, so you have to consider the square root of v, its derivative, and then so say KPZ-like renormalization. And then you also have this drift, this diffusion coefficient exponent 3/4. Now, again, I don't think that it is possible today to solve this equation because also regulated structures work with smooth coefficients. No? There is no version with the Hölder coefficients for the time being. But, okay, so what is very inspiring here is that, like for Yamada Watanabe in one-dimensional diffusion, so the exponent 3/4 has been proved to be the critical one for pathwise uniqueness, of course, forgetting the complicated term here. Okay, so Müller, Mittig, Perkins tell you that if you take a higher exponent, you have pathwise uniqueness. If you take a smaller exponent, you don't have pathwise uniqueness. So it's exactly as for Yamada Watanabe. Okay, so it looks like there is some. I know there is, in this crazy picture there is some consistency. Okay, so who knows? Now another dream is the following. So one of the motivations, again, I show you the nice simulation. Again, you see the stochastic heat equation here is essentially a Brownian bridge in space. So it hits very often 0, and so while the stochastic reflected heat equation is a three-dimensional Bessel bridge. So at fixed time, you don't heat at all, but you have the exceptional times, and you can heat maybe a lot, but the question is how much? How much, for instance, how many, how do you say, simultaneous heatings can you have at a fixed time t? Not that you fix the time, but at the same time t, how many simultaneous heatings can you have in space? So here you have infinitely many, uncountably many even. So this was a nice question that I was able to solve because I was helped by Robert Dalland and Carl Müller. So it turns out that for all delta greater or equal than 3, whenever k is an integer such that k is greater than 4 divided by delta minus 2, then there is, so the probability that you find the k simultaneous heatings is 0. So in particular for delta equal to 3, this is 1, so this is 4. Starting from 5, impossible. Okay, so this was a very very nice result, which we were very happy about. And when delta grows, you see that this decreases. It becomes 0. This becomes less than 1 when delta is equal to 6. So from 6 on, there is no heating. Okay, there is a transition from 4 to 3 to 2 to 1 to 0. But this is when delta increases. So what happens when delta decreases? Now, again, I allow myself to dream. So the formula is already ready. Okay. So when delta goes to 2, you have more and more simultaneous heatings. but always finitely many. And when delta is equal to 2, this becomes infinite. That would be a critical behavior. It may be infinitely many in the countable way, or in the uncountable way, etc. I have no idea. And again, it's clear because 2 is the critical dimension for the invariant measure to hit 0 or not. So yeah, okay. So I think, yeah, exactly. What about delta less than 2, in particular delta equal to 1? So of course you will probably have many hittings, but you have to imagine this contact set which evolves in some complicated way. It looks a very inspiring question. So all this is for the future, and so Henri is going to tell you about at least the integration by parts formula, and I stop here. Thank you very much.
Thank you very much.
So that was a great talk. So let me ask you, are there any examples of a random field, maybe a solution of an SPDE, where we know what kind of this local time measure is, this space-time local measure? I mean, do you have any examples? Well,
in the Gaussian case, you can prove, because you have special results for Gaussian processes. So for the heat equation is under control. For instance, okay.
So the question behind the question is there any chance, just like you do a speed measure and a natural scale, could you do a speed measure, a natural scale in space and time? Again, that's you use stochastic calculus, and this is based on the Ito formula. We are lost. It is too difficult. Again, the form of, as soon as you start taking Ito formula, this is just the power 4, and you already get a crazy term like that. So you see, the power 2 is the same. So you get these infinite terms. Yeah, but yeah, we need to understand this.
Other questions?
Do you know whether the last formula you have for the hitting, the number of hittings is sharp?
Thank you. No, so we have some, no. For instance, you expect this to be not strict inequality, but so this is only the negative result, okay? Then you should prove that if you are below the same value, the probability that you do have hittings is 1. So this we have only for integer dimensions, but it's not sharp. No. This is a very good problem, even for delta greater than 3. It's not no.
Other questions, remarks?
Just a question. So the delta equal to 3 process, is that fair to say that this is a little bit like an obstacle problem?
Yeah.
That's the obstacle problem.
Yes, so yes, absolutely, it is the obstacle problem.
So in my own intuition, so the number of times it hits should depend on the system size. Here you seem to get something universal, but that's because it's normalized.
I am on over 0,1, so if you take 0,10, no, it would be the same.
So
it will be the same. So it's just a scaling. It's a scaling like that, but it does not affect.
So would it make sense to think of the problem where you just pin one end and you're on the semi-axis?
Yes, that may change. I don't know. Okay.
Other questions? Remarks? If not, Lorenzo, we thank you very much.